Welcome to NASA Edge.
An inside and outside look
at all things NASA.
Hey, we got a great show lined up today. We're going to be talking about two cool technology demonstration missions.
TDMs, we've covered them in the past, great ones, Deep Space Atomic Clock, Medley, LDSD.
LDSD or Space Brakes.
Yes, that's right. I like your phrase.
Yes.
But on today's show, we're going to be focused on GPIM and eCryo.
That's right, GPIM, which is the Green Propellant Infusion Mission.
And eCryo is the Evolvable Cryogenics. And we're not talking about freezing somebody like in Star Wars with carbonite freezing. This is dealing with fuel.
That's a good point. You know, before we get to GPIM and eCryo, I had a chance to sit down with the Associate Administrator for the Space Technology Mission Director, Steve Jurczyk, and I asked him how GPIM and eCryo fits into his portfolio. So Steve, we're talking about two really cool technology demonstration missions today, but before we get to those missions, let's look at the overarching theme for Space Technology Mission Director. What are you all about?
We run the cross-cutting technology programs for the agency, where we're developing revolutionary transformative technologies to enable the future missions for NASA. And we're really trying to enable not only more capable robotic missions, but also human exploration of the solar system. Our technologies cut across a lot of areas, and we have these 8 thrust areas, and they range from everything from advanced in-space propulsion to advanced power systems, to environmental control and life support systems, and even precision navigation. And so those are the capabilities that we're going to need, particularly if we're going to do human exploration of Mars.
Right. Now, we have two cool ones today. The first one, of course, is GPIM, or the Green Propellant Infusion Mission. Tell us a little bit about that and how that fits into your portfolio.
Yeah, so GPIM is part of our propulsion system portfolio. It is leveraging technology that was developed by the Air Force, which is a green propellant that is not only safer for the environment, but also provides higher performance for propulsion systems. So it's been a great partnership, not only with the Air Force, but with Ball Aerospace and Technologies Corporation and Aerojet Rocketdyne. And it's just an example of a very cross-cutting technology. You know, one that can be used in not only spacecraft developed for NASA missions, but missions for other government agencies and the commercial industry in general.
And the other technology demonstration mission is eCryo. Where does that fit in your portfolio?
Yeah, so that's also a propulsion system technology, completely different though. What we're trying to do is a couple of things. One is hydrogen and oxygen are very low temperature. And if you don't insulate them in a system, they boil off and it just goes away. You can't fill the tank up fast enough to keep it full. So we're trying to develop technology to insulate the system so we can store propellant in orbit. And then we're also developing technology to transfer from a delivery spacecraft to another spacecraft. So this gives you operational flexibility. You can have upper stages, stay longer in orbit and refire them for more mission agility. And also it's part of our architecture to launch systems and reuse them in space.
Right.
So you use up the fuel, but it stays in space. You send up a fueling system and you refuel them and use them again.
So is it fair to say, Steve, that in STMD, you're looking at technologies that maybe relatively new, that you're just starting out maybe as a paper study, but then you have some technologies that are more mature that are ready for spaceflight?
Yeah, so our programs are organized like that. So we have a set of early stage programs. Space technology research grants are research with universities. So that tends to be what we call lower technology readiness level. And then we have what's called NASA Innovative Advanced Concepts. And we do a solicitation every year, and we get proposals from everywhere, NASA centers and universities and industry. And we get some really interesting kind of way out concepts, things like laser propulsion and mining asteroids for fuel and water. And so not many of them go on to the more mature projects, but it's really great to see the innovation that we get. And then we have the game-changing development program, which takes some of those ideas that are kind of way out there and matures them.
Right.
Then the ones that pan out of game-changing move on to technology demonstration missions like GPIM and eCryo.
So you're the guy to go to if someone has invented the lightsaber, warp drive.
Yep, we're always looking for warp drive. We're always looking for warp drive, infinite energy at zero mass and zero volume. Those are all the things we're always looking for. And so, yeah, if somebody has unobtainium out there, we want it. Yeah.
Look, guys, I got to say, you know, I really enjoyed talking with Steve, but he lost me in that last part, unobtainium. I'm not down with the times.
Well, I mean, you know, it's a good reference. It's a reference to Avatar. That's what they're mining on Pandora.
Okay.
So I give Steve a little bit of credit for
Showing
actually
us his sci-fi chops.
Yeah.
I mean, I would have said vibranium, adamantium, and that's more, you know.
Yeah, you're on that Marvel line.
Yeah.
You know.
As interesting as Marvel is, and as much as we love them, the technology we're going to talk about today, though, is still very cool and not hopefully unobtainable, but very attainable. Green propellant. It's green in that it's environmentally friendly, or friendlier than what we currently use. But the real expert on green propellant is Chris McLean at Ball Aerospace, and I had a chance to sit down with him and get all the details about the Green Propellant Infusion Mission. So Chris, I'm very excited about this Green Propellant Infusion Mission, but what exactly is green propellant?
Well, green propellant is a non-toxic fuel, relatively speaking, compared to heritage in-space propulsion technologies like hydrazine and hypergolics. What makes it really green is the fact that it has a very low vapor pressure. You can put a container of this stuff on your desk and there is no evolution of nasty species that might mess with your breathing and, get into your airways and stuff. And it actually, the toxicity of the liquid itself is really low. It's something you could almost drink, but not quite. We're also able to ship it at FedEx across the country. We don't have to have it in explosion-proof containers.
Could you, say, ship me some green propellant for my desk back at NASA?
Well, that's a nice idea, and we've been asked to do that before. However, it is still an explosive.
Oh,
so
well,
even though it has a low explosive handling rating for shipping, it's not something you'd probably want sitting around all the time. So
obviously, that has good. It's good to be green and obviously conscious in that way here on the planet. What kind of benefits does that add for space travel?
The green benefits aren't really part of the space application, right? It's for when we're handling it and loading it and providing protection to the technicians and engineers that work with this stuff. When you're working with this fuel, you really don't have to worry about exposure to it. If you spill some, you can clean it up with water and rags and things like that. When we're in space, the real benefit is the performance of this fuel. There are two things about this propellant that make it outstanding compared to heritage fuels. One is the performance is significantly better for a monopropellant. If we look at a hydrazine system, which is similar to what we're doing here in terms of a single fluid and rocket engines attached to that, this thing has 50% better performance. So if you can imagine your car had enough gas in a fuel tank to go 100 miles, well, for that same fuel tank, you go 150 miles with this fuel.
You've basically turned it into a hybrid vehicle.
All right, pretty much. And some of the other benefits are when we look at deep space missions, there are times when with a hydrazine system, you need to have heater power going all the time to keep the propellant from freezing. Because if it freezes, if hydrazine or any of the traditional propellants freeze, it expands like water, like ice in your ice cube tray, and it'll break lines and things like that. With this fuel, it goes through a glass transition phase and does not expand at all. So for certain power critical applications like going to the South Pole of Mars, which is an example, or landing on a comet, if you wanted to be there for a while, you could save energy and put it into the electronics and things that need that energy and not spend the resources keeping the fuel liquid, because you don't have to do that.
So what exactly is infusion of the Green Propellant Infusion Mission?
When we look at technologies that are employed on spacecraft are high dollar assets, for, especially the big geocoms. You can talk in $500 million or more for an asset like that. So in order to use a technology like this and take advantage of the performance benefits that are offered by it, you need to demonstrate that first. Almost every spacecraft that you will look at, they'll say, well, has this flown before? What's its history? What's its heritage on orbit? What is our experience base with it? So by flying this technology on this spacecraft, we build that experience base. A lot of it, in my mind, which kind of surprised me as I went through this process, was realizing, getting range safety familiar with it and the loading people saying, hey, this is a new fuel. We haven't had a new fuel go through some of the processing steps since 1972. So by the time we're done with this mission, we'll have characterized this fuel on orbit on a spacecraft, demonstrating that we can do all of the heritage applications of propulsion for a spacecraft, of moving it around, desaturating momentum wheels and pointing the spacecraft and things like that. And so we can say, hey, this technology is ready. It's ready for use on other applications. And as people start proposing spacecraft downstream, they can say, hey, they're in my catalog and my toolkit of things I can put into this proposal, into this spacecraft. Green propellant's been demonstrated, so we can use that.
I think this could be the first time, in my recollection, that the word green is used.
You sure?
Hey, he's really struggling with his certainty on this.
I think this is the first time that the word green is used in conjunction with a space technology. Is that fair to say?
I think that is fair, and additionally, all of the environmental benefits of this mission really take place here on Earth, but when they go to space, they're not compromising any performance, which is really awesome in terms of this being a good technology to be developed by NASA.
And speaking of going to space, we're actually going to cover the launch of GPIM along with the Deep Space Atomic Clock next year on a live show.
Yeah, I'm looking forward to that because I think that launch is going to take place down at NASA Kennedy, which we love covering launches live, don't we?
Sure.
Yes.
Now, speaking of technology, we talked about GPIM, great technology, but now we have to shift gears. We have another technology we need to talk about, which is Evolvable Cryogenics.
Right, and I had a chance to sit down with the eCryo program manager and my genius twin brother, Hans Hansen, to learn all about the many aspects of eCryo. So Hans, I noticed you have a lot of moving parts in the eCryo program, but there are a lot of things that are E this or E that, so I'm wondering what exactly is eCryo?
Sure. So eCryo is Evolvable Cryogenics. So we're looking to try to build on cryogenic fluid management technologies, or CFM, for in-space applications that can be scaled up to an upper stage or potentially a depot down the line, or even Mars applications. We're looking at either demonstrating technologies for the first time, or how can we scale it up to a larger scale so that it can be infused into a mission.
Now Hans, correct me if I'm wrong, but I always understood cryogenics as sort of that process where you freeze the astronauts so that they can live longer in space on their trip to Mars. That's not what's going on here.
No, we're not looking at cryogenics for that application. We're looking at it for...
So there is an application to do that. So, I'm sorry, go ahead.
We're looking at using cryogenics in storing fuels. So the reason we use cryogenics is they have a very high energy efficiency so that you can get the most bang for your buck, or best gas mileage, if you will.
It's important in space too, I guess.
Yeah, especially in space, because every pound matters. So what we're looking at is to try to see how can we be more efficient with storage of these fuels, because they have to be stored at such a cold temperature. We're trying to prevent the fluids from boiling off so you don't lose your fuel on your way to your mission.
Now, I was looking at your logo and I noticed you have a veritable plethora of acronyms there. Maybe it should be E-acronyms as your title.
Yeah, we have some talented team members who came up with a bunch of these acronyms, but our modeling effort is DVAT. It's development of and validation of analytical tools. That's where we're doing our modeling and simulation of the physics. We're also working on IFUSI, it's improved fundamental understanding of super insulation. So we're looking at a coupon level multi-layer insulation technologies that are used on spacecraft and upper stage tanks for long duration missions to try to extend the mission duration from a couple hours to maybe potentially even months if you're going to a Mars application. Shiver is our largest element of our project. It's a 4-meter tank where we're going to be testing liquid hydrogen type applications applicable to an upper stage.
Now what about RFMG? What's that all about? I tried to guess, but I can't quite get a handle.
RFMG is our radio frequency mass gauge. Once you get up in space in microgravity, you don't have a level sensing opportunity, so we're trying to use radio frequency to gauge how much fluid is in a tank.
You definitely want to know how close you are to E when you're ready to head back from Mars, right? What about IVF?
So IVF stands for Integrated Vehicle Fluids. This is a ULA-based proprietary technology that we're looking at doing some testing and assessment of the technology to see if it's applicable for the Space Launch Systems exploration upper stage. We're doing testing and analysis and modeling to see if it could save potentially a few thousand pounds up mass for the SLS program.
So essentially what you're saying is if eCryo is successful, that eventually we'll have a lean, mean spaceflight machine.
Yeah, we're trying to get as efficient as we can with our fluid management. The whole eCryo project is trying to understand how fluids operate in a microgravity environment.
One of the things that Hans also said is they're trying to get this technology to the point where they can actually test it in space, because once you know that the technology actually works in flight, then it can be a part of every NASA mission coming down the line. And that's really the goal of these technology demonstration missions.
And just like Hans said...
Oh, wait a minute. I'm sorry, forgot. I gotta mention this because Hans, my twin brother, actually told me that I needed to be sure that I made this point. Okay, I made the point in the interview. It's ridiculous. NASA's explicitly not involved in cryogenic research of that kind. It's ridiculous. But then last night, I was thinking when I couldn't sleep, I was like, eCryo, think about it in sci-fi, never a good idea. Not once do you watch a sci-fi movie where they have cryogenic sleep and you think, man, that's technology we need. It's always problematic, right? So not only does NASA not do it, but it's not even really helpful in the sci-fi community, right?
Continuing on. So if you remember in his interview with Hans, eCryo has a bunch of smaller projects that are kind of under the umbrella of eCryo.
That's true. That is true.
And one of them is called Shiver. And I had a chance to talk with Monica Guzik, the lead engineer for Shiver. And the cool thing about this, we had a chance to go out to the Plumbrook facility, which is about an hour from Glen, in a building called B2, where they had a thermal vac chamber. So Monica, shivers. Every time I hear that, I get cold. What's that all about?
Well, we did that on purpose.
Okay.
We're dealing with very cold stuff. We're actually dealing with cryogenic liquids. But SHIVER stands for Structural Heat Intercept Insulation and Vibration Evaluation Rig.
Okay, that's a mouthful, so you're gonna have to explain that to me.
So what's going on here is we've got liquid rocket propellant tanks, and they're cryogenic, which means really, really cold.
Right.
And we're storing cold liquids. So what happens when you have a cold liquid is anytime you get heat in, you start boiling it off, just like water on a stove.
Okay.
For us, boiling off is not a good thing because that means that we're losing fuel. Imagine trying to go drive to California with a leaky fuel tank and no gas stations in between. You're never going to get there.
Okay.
We have the same situation, so we're trying to plug that leak by preventing the heat from coming in.
And what are you using to prevent that leak?
So we're doing it two things, and that's right in the name. We're using structural heat interception, which
Okay.
means that we're actually cooling the structures. These tanks have to be held up by something,
Right.
and they're attached to really hot parts of the spacecraft.
Right.
So we're trying to cool those attachment points so that we reduce the heat coming
Okay.
through them. We're also using insulation to try to prevent radiation that's coming in from the surrounding space
Okay.
environment.
So now what kind of materials do you use to insulate the tank?
What we're using primarily is called multi-layer insulation, or MLI.
Right.
So once you're in orbit, you don't have air or anything hitting it. Your primary source of heat is what we call radiation.
Okay.
Radiation is heat coming in from a really hot source and kind of transmitting from that source to its surface.
Right.
We prevent that by using highly reflective sheets. You can think of it as almost like a mirror. They're reflecting that heat away and preventing that heat from getting in. So we have layers of what we call mylar, which is actually just a type of really, really thin plastic.
Right.
And we coat them with aluminum or some other reflective material on both sides. And they end up looking a lot like really, really thin tin foil.
Okay.
And we layer these up and we separate each layer by something that doesn't conduct a lot of heat and is really lightweight. And it actually looks like the veil material that a bride would have on her wedding day.
I guess what you got to determine is how thick that insulation is around the tanks?
Right. The more layers you add, the less heat can get in. But that means you're also adding more material, which is more mass.
Mass, right. So there's a
There's
trade-off.
a mass trade,
Okay.
right. Because mass is money when we launch. So we're trying to save mass without adding too much.
I mean, I can only imagine when the launch vehicle is taking off from the pad, it's shaking, it's vibrating. I mean, there's a chance that material can come off.
Yes, there is.
So do you have to do testing to make sure it stays on, or?
Yes, we do. And that's the vibration. The VER part of it is the vibration evaluation that we're looking at.
Right.
So what we're going to do first is we're going to test here in this B2 chamber.
So this is a thermal vac?
This is a thermal vacuum chamber
okay.
called B2.
Okay.
And so here we can test very large. We've actually tested full rocket stages here before, and it actually is capable of live firing rockets, although we're not going to do that here. We're going to keep everything from burning up.
So how do you actually do a thermal test? If I put your simulated tank in here, you got to close the door somehow, and so how do you heat up the temperature so it's in space conditions?
Right. So one thing that's funny is since we're so cold, actually just the temperature right now will heat up the tank.
Oh, wow.
So when we talk about it, we're going to take this tank, we're going to close it, and you can sort of see the top of what we call a cryo shroud behind me. Okay. And what we do is we can run either liquid or gaseous nitrogen through the tubes that are embedded in the shroud. And those tubes we can set so that they're a certain temperature that mimics what we'd encounter in a space environment. And it may in fact be colder than the air around us right now, but it's still very, very warm compared to the liquid in that tank.
You're not really worried about the thermal test on launch though, right?
Right.
This is more of in transit.
Yes.
Okay, but then on launch, you're worried about vibrations, acoustic noise, things of that.
So once we do our first thermal test and we see how does it perform, when we know it's working, when it's good, it hasn't shook or anything, we're going to take it over to our facility called the Reverberant Vibroacoustic Test Facility.
Okay, right.
And we put it in there, and there's a whole bunch of what look like big speakers on the wall, and they can emit vibration sounds, acoustic sounds, to the levels that we'd encounter in launch.
Okay. And that would be typical for the launch vehicle that it's going up on.
Exactly.
Okay.
Yes, and we actually have some of those launch profiles already, and we're going to use those when we do our testing with the Shiver tank.
I tell you what, it seems like Shiver is an extremely important program for the journey to Mars, because if we want to send humans to Mars one day, we don't want boil off, we don't want to lose the propellant. And so really you have a critical role to making sure that there's enough propellant to get to your destination.
Definitely, yes. You can imagine if you were trying to go somewhere and you run out of fuel halfway there. It's bad enough if you're in the middle of nowhere, in the country, but it's really bad if you're in the middle of space on the way to Mars. So you definitely need to make sure you have fuel in the tank there and back.
So as I was processing this interview with Monica, as I was looking at it, as I was evaluating, I kept thinking with this idea of boil off, this kind of cold, kind of boiling in space kind of temperatures, I was thinking, well, that doesn't make sense to me because water boils at 100 degrees Celsius, and that's hot, right? So that's hot, it's very hot, but it's very cold in space. So I'm wondering, how are things boiling off in space? Is there something on the spacecraft that's so hot? I may have missed it. She may have addressed it, but I'm just curious if you dealt with this.
Different liquids have different boiling points. So just like you said with water boils at 100 degrees Celsius or 212 degrees Fahrenheit, right? So we're talking about cryogenic fuels. We're talking about really cold temperatures, in the minus 300 to 400 degrees range, right? So it doesn't take very much to boil those liquids off. So if you have something a little bit warmer than that, it could boil off.
So warmer is a relative term, warmer than that extremely cold. So from going from extremely cold to just slightly less extremely cold equals boil off.
This is where the multi-layer insulation comes in, because you have to make sure that you maintain that temperature inside the tank so that you don't get that boil off.
And so you just keep slapping layer after layer after layer after layer after layer on there until you get that sucker nice and comfortable, so there's no uncomfortable boil off. So okay, I got it. Now that's interesting, right? That's total interesting topic. Here's another question, because I'm wondering if you're curious like I am. Have you ever wondered, especially if we're talking about the fuels, you ever seen the ISS when the astronauts are up there and they've got the little water droplets and they're floating around and everything? And it's cool, right? It's fascinating. If you ever wondered, what happens to the fuel in the tank? When it's full, I get it. There's no room for anything to move around, but as you start to use that full, does it turn into little globs and start floating around inside the tank? Does that happen? Is that possible?
That's a great question.
Exactly, which is exactly the question I brought up with our good friend Greg Zimmerli, who's actually working on a technology to find out how to measure fuel inside a tank when it is floating around inside there. Let's check it out. Greg, before we get into the radio frequency element of your program, I'm just curious, I understand there's a challenge in measuring the quantity or amount of fuel in a tank in zero gravity. What is the challenge? What's exactly going on here?
Well, in 1G, or in Earth's gravity, the fluid settles to the bottom of the container, so we're able to use what we call a level sensor to sense how much liquid is in the tank. But in zero gravity, surface tension forces, other things like that, they can move the fluid around inside the tank to places where you're not sure where it's going to be. So we're working on a technique that can measure the quantity of liquid in the tank no matter where it is.
Now, correct me if I'm wrong, and believe me, most of the time I am, but it seems like it'd be kind of tricky to put anything that emits any kind of frequency in a fuel tank, because it might be, combustible or something. How are you accomplishing this?
The technique we're using, the radio frequency mass gauge, we put an antenna inside of a tank and we transmit a range of radio frequencies through the antenna. Those frequencies emit radio waves inside the tank, and it creates modes, natural electromagnetic modes inside the tank. And we measure those modes with a special instrument. It's very low power, there's no dangers with the technique.
So have you done any testing on this technology so far?
We've done a lot of testing here at Glenn Research Center. We've tested the technology in liquid hydrogen, liquid oxygen, liquid methane. We've also tested it on the parabolic aircraft.
Yeah, that's for the lower gravity situation.
The low G, right. So we get to about 20 seconds of low gravity on the parabolic aircraft. We weren't using the cryogenic fluids there. We were using a room temperature simulant fluid for those.
Well, now it's interesting you mentioned all those different test fuels. Did they behave differently in zero G?
In zero G, they'll behave a little bit differently because the surface tension of all those fluids is a little bit different. For example, water has a very high surface tension. but liquid hydrogen has a very low surface tension. So in that respect, they're different. But the only real difference for the radio frequency mass gauge is a property called the dielectric constant, which is...
All right,
well,
so you just moved above my grade of understanding, but...
Maybe I should say the index of refraction of the fluid. For example, glass and water slows the speed of light at different rates, for example, okay? So these fluids also slow the speed of light in a known way, and that's called the index of refraction of the fluid. So the radio frequency mass gauge is sensitive to that index of refraction. It slows down the speed of light. It changes these mode frequencies of the tank in a way that we can predict. So we measure those frequencies, and then we compare those to some simulations that we do on the ground ahead of time. And then we use, it's almost like a digital fingerprinting matching technique, okay? So we compare the spectrum of the tank that we measure with what we've calculated, and we find the best match, and then that tells us approximately how much fuel is inside the tank. The technique actually, it works relatively quickly. We can gauge a tank in a few seconds, for example. So you could gauge it as often as you want. You could have a real-time gauge that's showing how much liquid is in the tank.
But this is really exciting. I love this, but I'm curious now, how are they measuring it now?
So for the cryogenic propellants, there is no way currently to measure how much fuel is in the tanks when it's in low gravity. So we have to resort to secondary techniques that we call bookkeeping, for example. So we know how much fuel we started out with or how much propellant. We know how much we've used when we do engine burns, things like that. So it's sort of an accounting technique. So we call it the bookkeeping technique.
Wow. So it seems like this technology will actually go a long way and not just being more efficient, but giving a lot of confidence to mission planners in terms of knowing how much fuel they need and how much they have at any given moment.
That's right. It's sort of an enabling technology.
Is it fair to say that as you increase the size of the tank, you scale it up, that you would have to put more antennas inside the tank?
Scale up more antennas. My first impression, just based on Greg's expertise and everything I listened to in the interview and just my overall thoughts of the whole process would be, no more, and you don't need more antennas. What you really need, bigger antennas. Scale up, bigger antennas. You don't need more antennas, just bigger antennas.
Okay, as we wrap up the show, we talked about two great...
Wait. Before we get to the end of the show, I've got more stuff from our good buddy Hans, who's got more information.
Okay, go ahead.
So Hans said he had some very key information, and I was supposed to mention it earlier, and I think I did, but I don't think I did a good enough job, so I just want to go through it real quickly here. He says that, all these things in eCryo and the various parts like Infusey and Shiver and DVAT, which is a modeling component that we did not talk about. These are not just like all similar groups that are studying. They're studying it at different phases. So here's what he says. He says they're testing at the coupon level with Infusey. That's a smaller level. They're doing scalability with Shiver. Right. And then they're performing predictive modeling with DVAT, all moving toward getting that space test eventually so that it can be proved in space and therefore put in future missions. Thank you. Through email, last minute communication, nailed it.
Okay, so as we wrap up the show, we talked about GPIM earlier in the show. And remember in the interview with Chris McLean that...
Great guy. Great guy. Looks like the bad guy in Heroes. Remember the guy with the glasses? The cheerleader turned out being a good guy.
So remember that Chris said that he couldn't get a hold of some green propellant infusion mission?
Right.
It's peachy color.
Right.
What is that on the table?
What is that?
This, my friends, energy drink. I was concerned that I would not be able to perform to scalability with these TDMs, so I went out and purchased an energy drink, so I would have the caffeine to do well in the show today.
So that's not GPIM. I just want to clarify it, because you can't drink it.
Nobody can drink GPIM. That's bad. It's like not healthy. It's something that you could get close. You could spill in a shop and wipe up with a sponge or something like that. But you wouldn't want to make it a beverage on like a drink list, or you wouldn't want to bring it to parties, or you wouldn't want to offer it to your friend, or you wouldn't want to give it to someone who's thirsty, because that would be cruel.
Are you done?
I could be.
You're watching NASA Edge, an inside and outside look at all things NASA.
That better not be GP.
Oh, no. It's just an energy drink. Who would drink green propellant? It's not good for the environment inside your body. It's like bad. It's not green for the intestines.